In the 1960s, a small group of scientists had a big goal. A goal that would revolutionize civilization and mankind if accomplished. They wanted to replicate human intelligence, and they thought they could. Around 1957, Herbert Simon, one of the founders of AI, predicted that in just 10 years, there could be AI that could beat grandmasters in chess, or discover new mathematical theorems, or produce music of considerable aesthetic value. And clearly he was wrong. It took a lot more time to do that. And so the AI researchers at the time, they just gave up because the task of AGI was just too hard. They could not make something that had artificial general intelligence, also known as strong AI. And so they moved on. And from their defeat emerged the narrow AI that we're so familiar with today. So for example, DeepMind's AlphaGo, AI models that can identify cancer, or AI models that can speak and talk. These are all accomplishments of AI that we're familiar with today, but none of these models actually possess general intelligence. So can you imagine even one of these models try to do 1% of what you do every day? Probably not, because these models, this narrow AI, is only good at pretending to have intelligence. It's good at, it's able to do a small set of intelligent yet difficult tasks really well, but narrow AI lacks that special something that separates humans from every other animal on this planet. But where can we find that special something? According to most people, it's in the area where we know intelligence exists for certain, our brain. So our brain is incredibly powerful. Think back to the intro to this presentation. I was talking about the field of AI and its original goals and aspirations, but all I had on the screen were circles, and somehow you guys understood what I was talking about. So the brain is incredibly powerful, and many researchers have made it their job to study the brain, to research it, in order to create a model that replicates human intelligence and that has some semblance of human intelligence. And so today I'll be talking about a model, an AI model, that replicates the frontal lobe of the human brain, which is the area responsible for abstract reasoning and high-level thought. And so this model is called DORA, which stands for Discovery of Relations Through Analogy. And it's incredibly powerful. When we think about AI, when we think about scary AI, like AI that's going to take over our job, that's going to conquer the world or whatever, that's going to be eventually something that AGI could do. And DORA, in the future, could possibly have artificial general intelligence. And so, at a really high level, the way DORA works is by comparing stuff and then getting useful information from those comparisons. So if we follow the name, it discovers relations, which could be like the color red or the concept above through analogy or comparison. And so the model starts with a pool of objects and features. So for example, a fire truck and an apple. And it then compares them. And so comparison basically entails extracting the similarities between the two objects and encoding them into a unit. So right now, this unit isn't really that useful because it's literally just the similarities between the two objects, which is, in this case, red and kind of shiny. But over time, these units get more refined so that they only encode a single attribute or relation, like just red. And so it doesn't just have to be an attribute like red, it can also be a more complex relation, like the concept of higher or above, which requires two objects to make sense. And so then DORA just keeps on accumulating more of these relations and attributes, and it just becomes more and more powerful because it's able to understand the environment around it better. And so it's a steady state model. You can feed it new information at any time, but it only stops when it's told to stop. So for my replicate, I remade the DORA model and made it able to, I applied it in a game generalization context. So DORA was able to learn representations of the game Breakout, and then it played the game. And then it moved on to the game Pong, and it played the game. Without ever having looked at the game before, without ever having seen it, without having trained on it, it was able to play the game Pong using the representations it learned from Breakout. And DORA outperformed both humans and DeepMind neural networks that were trained on both games. And it outperformed them without ever having seen Pong before. So the way this worked is DORA was outfitted with two extra accessories, a visual preprocessor and a tabular Q-learning reinforcement algorithm. So the visual preprocessor just populates the objects and features that DORA needs to work. So for example, it takes these objects and features and it learns representations from them. And then as it gains more and more of these representations, it's able to characterize the game screen through relations. So instead of seeing this screen as like a ball in this specific position and a paddle in this specific position, like a computer would or a visual preprocessor would, it actually saw the game screen in terms of relations. So it would see like this ball is above and to the right of the paddle. And this becomes extremely, extremely powerful because not only is it kind of seeing the game screen like a human would, extracting the important information from it, that information is way more condensed and way more valuable. So when we get to the reinforcement learning algorithm, it's able to learn incredibly fast and way more efficiently. So speaking about the reinforcement learning algorithm, quick reinforcement learning crash course, there's an agent and an environment trying to get a reward. And it gets those rewards through state action pairs. So it's always in a state, and it's trying to figure out which action would lead to a reward. And essentially, through basically what is trial and error, it finds out which state action pairs generally leads to a reward. And it's able to play the game one state action pair at a time. And so with all of this in mind, we can finally understand how DORA was able to do this. So the visual preprocessor creates the objects and features that DORA is learning from. And then DORA learns those representations to be able to characterize a game screen, a breakout. And then the reinforcement learning algorithm is able to learn incredibly efficiently because the representations are so condensed and contain a lot of useful information. And from that, it's actually able to generalize. So Pawn and Breakout, they're pretty similar games. They have the same like mechanics, but Pawn is basically just vertical breakout because the paddles are on the vertical axis instead of on the horizontal axis. So when DORA encounters the Pawn game screen, it recognizes that even though the pixels are in different positions and it's basically just a flipped version, it recognizes that it's essentially the same thing because it has the same general relational concept, paddles hitting balls. And so the reinforcement learning algorithm doesn't have to change as well either. And DORA is able to play the game Pawn without ever having seen it before. And so, DORA is incredibly powerful. And if we think about it, for example, for a second, about what lies in DORA's future, there's so many possibilities, so many options DORA can go into in the future because of how close it resembles the frontal lobe of the brain. So, for example, DORA could possess metacognition in the future. In other words, learning how it learns. And metacognition is one of the 4 key steps Ben Goertzel, one of the founders of AGI, said would be necessary to actually create an artificial general intelligence system. And DORA has also shown incredible promise in areas like natural language processing, or object recognition, or abstract reasoning. And also, if we think about just DORA in this specific replicate context, DORA could in the future make a smarter reinforcement learning algorithm. So right now, the Q-learning algorithm it used was kind of dumb. But what if the reward function that characterizes the Q-learning algorithm could be based off the predicates and the relations that DORA learns itself? So DORA is incredibly powerful because of how close it resembles the frontal lobe of the brain. And in the future, I believe that DORA or a DORA-like system could actually possess artificial general intelligence.